Get started. Good. So setup is done. So our second speaker today is Hidaka, and he will tell us about Hamiltonian lattice gauge theory via TQFT. Right. Whenever you're ready, please take it.
Okay, thank you for the introduction. So first of all, I'd like to thank organizers for inviting me to very nice workshop and giving me opportunity to give a talk. So today, I'd like to introduce our recent work on the Hamiltonian lattice gauge theory. The reference is here. And first, I will give some review of the formulation that is called the Kogut-Susskind Hamiltonian formalism. And I will show you some gauge invariant Hilbert space and relation between the TQFT. So here, TQFT, roughly speaking, the generalized global symmetry. And this is kind of application of the generalized global symmetry to calculate the Hamiltonian lattice gauge theory. And the last part is ongoing work. So recently, I tried to derive some non-abelian dual theory of non-abelian gauge theory. What? In just particular for the 2+1 dimension. So my motivation is actually to understand the QCD, in particular the real-time evolution and the finite density system. So where
Most like this to say it's too warm outside. Don't
too warm. Okay. So it's very hard to simulate on the lattice gauge theory in the usual sense. That is Lagrangian formulation. That is real-time evolution and finite density is very difficult because it's so-called the sign problem. So here is an alternative approach to solve the lattice QCD by using the Hamiltonian formulation. So that is there is some advantage. So recently, there are many techniques of the so-called tensor network, and also the near future we can use a quantum computer. That is useful formality for to simulate. So the difficulty of the lattice non-abelian gauge theory, because of this is a gauge theory, so there are a very huge redundancy coming from the gauge symmetry. And also the local Hilbert space itself is also the infinite dimensional Hilbert space. Because roughly speaking, the gluon is a boson. So I will later introduce some regularization schemes to kind of the gauge regularization that respects the gauge symmetry. So, okay, let me start with the formulation. So the formulation itself is developed in 1975. So we know, so this is based on the L0 gauge, temporal gauge. And in continuum theory, and here is Lattice. So we have the commutation relation. We have canonical commutation relation and also the Gauss constraint. So physical set must satisfy the Gauss constraint. And Hamiltonian is something like something like this. So this is a continuum theory. So we can regularize this continuum theory on the lattice. Here, this is the Hamiltonian formulation. So time is continuous, but space is discrete. So we have something like the lattice. And as usual, the degree freedom, so A becomes some kind of link variable here. U. So U is roughly speaking exponential A. So that is a Wilson line. And also the E, so electric field becomes some kind of two types of degree of freedom. So usually we write I, L, and R. So that's this operator acts the link variable from the left and right. So since the link variable has something like the non-local degree freedom, so this operator acting from the left and this operator acting from the right. So of course, in the continuous theory, there is the only one degree freedom, which means this operator is related, not independent, but related to the transport. Parallel transport. Something like this. So left degree freedom is related to the right degree freedom related to the L through the adjoint link variable of the adjoint representation. And the commutation relation becomes a bit complicated. So originally, this commutation relation is regularized to the something like this. So this degree freedom lives on some link. So let's say this link is E. So commutation relation between the E and the E prime gives you something like this. So here TA is a real algebra. And U is actually the matrix. This is 2 by 2 matrix. So I use some kind of a matrix notation in this here. And so right operator gives you some transformation from the right. And similarly, you can define the left action like this. So this gives you some left transformation. And this operator itself has some commutation relation. Similarly, L this L and R satisfy the Lie algebra. So actually, we have some minus sign here. That is just a convention. So you can redefine the minus L as a L, then both satisfy the same commutation relation. But I use this kind of notation.
So little e prime are side index.
This is the index for the link. link there.
Oh, okay. But so L and R are defined on the site or the link?
Yeah, roughly speaking, so we have some site link.
Yeah.
So actually, this is the directly direct some direction. So the starting point and end point.
Yeah.
And roughly speaking, the L and R defined on the some link with the end point or starting point.
Okay.
So basically the link variable here, the index is L with some arrow. Okay. So this is the commutation relation. So actually, this gives us some algebra on the some one link. Then Gauss law operator G becomes something like this. So G defines some each vertex. And that is equal to so roughly speaking, so each vertex. So I consider the term direct lattice. So we have some direction arrow. So for example, if you focus on this vertex, V. So here E is a set of edge. So R corresponds to the starting point. So this means that, yeah, if you pick up this vertex, so we have some initial link, link with the initial vertex and outgoing and incoming. So for outgoing, we put the R here, and for incoming, we put L here. And sum over these one. So this is a Gauss law constraint. So this is a regularized version of this covariance derivative. So because the R is related to the parallel transport, then that corresponds to that G. So physical states must satisfy the physical state must satisfy this is equal to 0. That is a Gauss law constraint on the lattice. Okay. And also by definition, so this L and R and L satisfy this commutation relation, which means Gauss law constraint itself satisfy the same commutation relation. And actually, this is a generator of the gate transformation. So this is a
So the electric fields are the components of the field strength.
field strength tensor.
Why don't we write it?
E.
Yeah.
E is so actually this is a Hamiltonian formulation. So usually the E is a bracket of the time direction. Yeah, time direction. So now we take the temporal gauge. And now on the Hamiltonian formulation, E is some kind of local operator. Not the bracket. On the other hand, B is actually the bracket. So we can define the Hamiltonian on the lattice. And also the important point. So there is some constraint. So since this property, you can calculate the square of L is equal. You can show the from this relation, square of L and is equal to the R. You can easily derive this relation because this is unitary operator. So which means, so as long as if you are interested in the square, then you can don't care about the L or R. So in this sense, we use some notation just in square. So then we have something like this. So this is the Hamiltonian. Maybe I just put the coupling constant J. And okay. So this is the action. So here, F is a set of traces. So this is F is a set of traces, means a set of this bracket. And this is a kind of minimal action. So the UF, so UF is just a so Wilson loop. So in this case, just simple notation. So for each base, we have each bracket, we have a bracket degree freedom given by this one. This is just a Wilson loop. So this is the action. So in continuous language, this J is related to the 2G square times, I don't remember the detail, but this is related to the original coupling constant, and K is something like G, 2G over 1 or something. But yeah, but I just use some general coupling constant for simplicity. This is a basic Hamiltonian in this formulation. And commutation relation. So now we want to solve. So the Hilbert space is given by the representation of this algebra. So let's consider some let's consider some local Hilbert space defined on the link. That is a basic degree of freedom on lattice. So we have some one link here, and so we want to consider the Hilbert space on this link. So we have some did algebra. So if we have algebra, so we can represent the state, the basis of state by using the mutually commuting operator. Eigenstate of the mutually commuting operator. So one choice is actually just a Wilson line. So you can diagonalize the this operator. So formally, this operator has some index. So sorry, I said 2 by 2. But in FEN case, this is an n times n matrix.
So, by the way, the commutation relation, can I view it as seed for the work form electrics, work form symmetry action?
one form symmetry action.
Yeah, so basically L or R are the local operator projection of what would have been F0I components.
Yeah.
And that will be the generator of the electron one form symmetry.
I will discuss generator with higher symmetry. Yeah.
Okay.
Right. Yeah. But I here. So this is generally n-type symmetry for SUN. And this Fijk is a structure constant. So you can diagonalize this operator by using the element of the group. Here, G is some element of the group. So that is something like the representation matrix. So more generally, you can consider the Wilson line with some representation. So this A here is a label of. So we have some fundamental representation or adjoint representation and so on. So in general, Wilson line has some label A that corresponds to the representation. Then if you apply this operator on some state represented by the group element, so that gives you the some matrix. Like this. So this basis is used for the ordinary lattice simulation in the Lagrangian formulation. So you can use this basis, but it is not so useful to solve the Gauss law constraint. So alternatively, you can use another basis. Let's say this is the magnetic. Yeah. So another basis that is eigenstate of the sum of these operators. So as a concrete example, let's consider the SU2 case. So this SU2 case, this is nothing but the algebra of the angular momentum. So we just choose the square. This is the second Casimir, and the third component of the real algebra. So in this case, so and also the L and R are somewhat independent. So here L and R are commute each other. So you can diagonalize both of them. However, so there is some constraint coming from this one. So actually this is equal. So which means the physical state is labeled by this one and this and this. So we can write something J and N and N. So which are the eigenstate of this one. Okay, that's somewhat obvious. So you can generalize any Lie group. Just it is just a representation of the Lie group. Okay. So now we get some local Hilbert space. So actually, this Hilbert space is actually the isomorphic to the L2 function with U2 is somewhat isomorphic to the direct sum. J. So Qj is some Hilbert space given fixed J, and this since we have the L and R, so we have the Hilbert space of this. So this direct sum is equivalent isomorphic to the S2 function of the Hilbert space for SU2. So these are just a dual basis. These two are just a dual. They are related to the Fourier transformation. Okay. And also so from this commutation relation is one. So we can also express this Jn state by using the U. You can from this commutation relation, you can easily show this operator is related to the here dA is just a dimension of the each Hilbert space. So I use the ABC that just a label for the representation. So A is just a J. So which means so Wilson line, there is some correspondence between the Wilson line and some physical state. Not actually this is not physical state, but some state. So there is some correspondence between the state and Wilson line operator. So we can use this relation interchangeably, which means we just write this operator something like this. So this is some Wilson line of the whose representation is A, and here is M and N. So if you write this like this, this corresponds to this operator or this industry. So this is somewhat useful to use some graphical calculus. Okay. So this is the basics of the local Hilbert space. Now we want to consider the Hilbert space for the gauge theory. Okay.
I have one question.
Yes.
So in this case, how is the gauge parameter?
Gauge.
What is the gauge parameter?
So what is the gauge parameter?
A to A plus B.
gauge theory, yes.
gauge theory. So there must be something corresponding to the gauge the gauge transmission.
Gauge transformation, yes. Okay, there is some, you mean the question is what is the gauge transformation?
Yeah, and
So actually the gauge transformation is generated by this G. So actually, if you just have this lattice system, then gauge operator is just something like this is endpoint. That is just L I, and gauge transformation operator is just something like DI. And you can ask this operator on this state. So here, this is just a single point here. So that is if you ask this state, then you will get something like maybe U is a link variable, so maybe it will be divided by B. Among J, D. This is L, so M, K. The gauge transformation is given by something like this. This is just a rotation. This is just a representation matrix. Like this. Well, this is just an endpoint. So now gauge theory is some lattice. So if you add here, so in this case, so this operator becomes something like Li minus R. Sorry, my notation is this is minus and minus n. So gauge invariant state. So in this case, there is no gauge invariant state because there is no invariant state under this transformation. So on the other hand, if you have the two links, you can consider the gauge invariant state on the two links for this matrix. So it can be easily obtained because this is just a generator with SU2 or SUN. The invariant state means that this state must invariant singlet on this matrix. So in this case, we have something like so singlet state can be easily obtained just summing over the intermediate state in this case. So let's say this is A and B link here. So summing over the all internal degree freedom gives you the invariant state. So you can apply this operator on this state, then you can get the zero because this is singlet combination. Okay. So this is a 2-point vertex. That is easy. So you can generate a 3-point vertex. Yes.
Little g. Little g is like the group element that you get in SNMG data.
Yeah.
So it's like the gauge transformation.
This is a gauge transformation.
Parameter.
Yeah.
And then In the second line, you want to sum over K and N,
K,
or just K?
K is
That K, but then you're only summing over K.
sum over, yeah, so we have two vertex. So now I just impose a gate transformation on this vertex. Yeah, just here. So you can also impose, consider this transformation. So since the gate transformation is a local transformation, so you can choose any point. So now, consider some 3-point vertex. That is also easy. Let's say A, B, C. And in this case, somewhat my notation. So since we have the two going vertex and incoming vertex, so then we have this kind. So here is B. So we have this operator. And each local Hilbert space is given by JA. So this is each local Hilbert space. So this is not gauge invariant. So we want to find a gauge invariant combination of this. That is easy. So with some normalization here, plus just you put the Krebs-Gordon coefficient. So this is just a Krebs-Gordon coefficient times some normalization factor. So normalization itself is not so important. The important point is that Krebs-Gordon coefficient is an invariant tensor under this transformation. More precisely, yeah. So which means if you multiply the local state by the Krebs-Gordon coefficient, then you will get the gauge invariant state on this vertex. So you can do the this procedure for the any vertices, any vertex, then you will get the some gauge invariant Hilbert space. The basis of the gauge invariant Hilbert space. That is the simple procedure. So as a result, so if you have some kind of honeycomb lattice for simplicity, then imposing the gauge invariant condition, then the Hilbert space is actually the labeled by, so since these internal degree freedom is summing over the by the Krebs-Gordon coefficient, so the remaining degree freedom is just J. So in this case, you can just put the sum J1 and J2 and J3 and J4 and blah blah blah. Then that becomes the basis for the gauge invariant Hilbert space. But of course, not all Krebs-Gordon coefficients exist. So this JABC must satisfy some condition. So JABC must be the integer, or that is a non-negative integer. And also this operator satisfies the triangle relation. So if you see the some vertex, these vertex, so representation must satisfy this relation.
Ask a question.
Yes.
Would it still work on a cubic lattice?
Hmm?
Does all of this work on a cubic lattice? You just pick the honeycomb lattice.
Yeah, cubic lattice is also works, but we have to careful because the Gaussian constraint does not fix the all degree freedom. There is some so if you have a 4-point vertex, so imposing the Gaussian constraint, then there exists some non-trivial internal degree freedom that can be decomposed into the something like this kind of that, or other just a vertex.
Yeah.
And you can just put a similar quantum number. Then, yeah.
And the reason that I asked is I remember hearing from lattice folk that if you use a hypercubic lattice or a cubic lattice, you're guaranteed to, in a continuum limit, if one exists, get to a Lorentz invariant theory because it has such a large lattice symmetry.
Yeah,
But
okay.
if you use other lattices, this is less up.
Okay, yeah, but yeah, you can just use the Hamiltonian lattice, but you can just introduce the auxiliary line. So in this sense, so I would say there is no action of the electric field on this lattice.
I see.
Yeah.
You introduce some auxiliary. Okay,
Yeah.
thank you.
So this is for SU2. So if you consider SU3 or higher n, then we have additional degree freedom. So you know the correction coefficient has some additional index that corresponds to the multiplicity. So in general, you know, SU2 has no multiplicity, but JMN just determines the whole degree freedom. But in general case, we have some additional degree freedom. So that corresponds to the some index for the vertex. And so in general, we can write down the any Hilbert space of the lattice gauge theory with some level on the right link and with some vertex. That is general. So this index is somewhat complicated. So yeah, we mainly focus on the SU2.
Right. Can I ask another question? Just for orientation purposes, like how do you plan to use this formulation of lattice gauge theory? Like like the conventional space-time lattice.
Yeah.
You could put in a computer.
Yeah.
What is the dream with this?
Yeah, I want to put this formulation on the computer.
On the computer.
Yeah. But still, you know, this Hilbert space is infinite, so it's not easy to put this one. But we can regularize this Hilbert space by using the quantum deformation.
Okay.
Then, if you use a quantum group, then this Hilbert space becomes some finite dimensional Hilbert space.
Do you want to put it on a quantum computer or normal?
Both.
Both.
Yeah.
Great.
Yeah. Yeah. So this the reason why I use this formulation is that, you know, if we don't do this constraint, then Hilbert space is really huge. Because coming from the gauging random. So far, classical computer is not powerful but not so very powerful. Then it's better to use this constraint, solving constraint. That reduces the significantly reduce the dimension of the Hilbert space. Okay. Then we get the Hilbert space. So now, so here this is just a Hilbert space. So what we need some operation. So we need to know the action of operator onto this yield space. So for this purpose, we need some fusion loop for the Wilson line and the electric field. So there is some relation between the operator and the state. To consider the action, so it is enough to think about the product of the Wilson line. A so we have two product of the. So this is a product on the single lattice, a single link. So from the transformation property, you can decompose this Wilson line by using the another Wilson line thing. So with some coefficient. The coefficient is again obtained by the just flexible coefficient. So we have some two flexible coefficients. The index is somewhat complicated. So I omit here. Not so very complicated. So I think. So yeah. So if you have the two Wilson line and whose product is given by this one. So you can show that this relation from the by using the group theory. So this in graphical notation, you can just write two Wilson line A and B. So remember this line, the normalization in this line, we have some square root dA, just some normalization. So that gives you some non-trivial coefficient. So in the graphical notation, you can write something like this. This factor coming from the state, so that line corresponds to the root of dA. So one line corresponds to this normalization. So we have some non-trivial line here. So this is kind of vertex. So this vertex corresponds to the flexible coefficient here. So if you have some vertex, then that represents the flexible coefficient. That is nothing but here. So this is a kind of the fusion rule for the Wilson line. And also similar relation can be obtained if you have this kind of diagram. This is the relation. if you have this kind of diagram, then you can evaluate this diagram by this.
The A and B lines, do they live on the same lane?
Same, now it's the same way. Then you just evaluate this operator. Then, so this is kind of the OPE on the lattice. So lattice, since this is lattice, so everything is well defined. And also the another diagram that is somewhat important, but a bit non-trivial. So similarly, you can consider this kind of diagram. So this is not a diagram for one link. Let's say just a 3 link. One link here and 2 link. First link here and second link here and third link here. And good product. So this is equal to this is equal to this diagram. So this is some kind of network algebra for the Wilson line. So this F is called the F symbol. And this can be written in the case of SE2, the explicit form is known. So expression itself is not so important. So there is some yeah. In the case of SE2, there is some explicit expression. So here, this is a 6-day symbol. Yeah. So if there is some topological phase in SU2 gauge theory, so Wilson line is satisfied with this kind of topological relation. And also this and this. So actually, this is the basic algebra for the SU2 gauge theory. So you can generalize this to the any SU-N gauge theory. And also more precisely, we have some additional information coming from the grading. So if you have this kind of diagram, ABC, so this is usually something like ABC. This gives you some information with the exchange of the state. That is the grading. So these are basic information, and also we need some additional constraints. coming from the consistency condition of the D diagram. That is sometimes called the pentagon equation and so on. So,
I have one question.
yes,
So they are on the grading, they are actually on the defined on the same book, right?
same link.
Well,
Yeah.
how can we define the grade?
So to define the grading, we need the two links. At least, yeah. Sorry, three, yeah. Two or at least two links, yeah.
Then, you define the link, yeah, something.
Something, yeah.
So for me, the A and B.
Yeah, something like that. Okay, so this is a basic algebra for the FU lattice division. So now, so from this notion, we can evaluate the action of the operator on the on the physical state. So we have Hamiltonian in J in something like D square something like this. Then for E square, if you have some link variable that acting on the link, but this is labeled link. So that gives you the second Kashmir. And one on trivially, so if you act the Wilson loop operator on this thing, the this algebra gives you something like some product of F. So I omit index. That is some just complicated. But the point is that the action of the Wilson loop on this network is given by this F. So I just give you some sketch of the calculation for this vertex by using the graphical algebra. So you can forget this one. So we have this kind of lattice. So any lattice is okay, but just for simplicity, consider this kind of lattice, a bracket. Then the action of Wilson line, so you just put the loop here. Okay. So this is a graphical notation. So if you consider this operation, just put this U on this vertex. Then, so we can use this kind of relation. So first, so if you use this line here, then this line becomes something like this. So suppose there is a defect here. You cannot cross this line.
What do you mean by a defect?
Yeah, so precisely speaking, your own lattice there is no defect, but lattice itself has some hole. You can forget this one. Just using the operator algebra, you get this relation. But yeah, just I want to explain that graphically, you can calculate this one. So suppose there is some defect here. So where we cannot cross the Wilson line. So that corresponds to the holonomy of the dividend equation. Then you can fuse this line. Then you will get this coefficient of DDD here. Then you move this line from here to here. Then you will get some F here. So now I move this line from here to here. Then that corresponds to this move. Then you will get some F here. The similar operation can be done for each vertex. Then we get F, 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 F. So since we have the 4 vertices, so now become the sphere becomes something like this. So since I moved here and here and here and here, then we get this kind of diagram. Then you can shrink it by using this relation. Then we get the additional DDD here. That cancels this one. Then eventually we get the 4x with some coefficient. So this is the basic calculus for the lattice gauge theorem. Maybe it's the time stop here. It's in the break there.
Okay.
So
10 minutes is okay?
Mhm.
10 minutes is
I
okay.
define here.
Okay, so we're gonna take a 10-minute break and then we will resume at 4:15.
Okay, let's get started.
Gain invariant Hilbert space and action of the operators. So here I want to introduce some several gain invariant operators on the lattice. There are many gain invariant operators, but the basic one is a Wilson line, a Wilson root. So that is just not trace of the some representation on some thing. P is just a side group, something like this. And also there is another operator that is called a coefficient operator. So on the lattice, graphically that corresponds to the line operator on their lattice. So dual lattice means, so if you have the lattice, then you have some dual lattice like this. And the coefficient operator corresponds to the line operator on this one. And this is labeled by the some conjugacy class of G. So the conjugacy class is defined by the conjugacy class of G is defined by the element of the group. this is a conjugacy class. This is a representative of the conjugacy class. And the fit operator is defined by this label. The meaning of this one is explained as follows. So the shortest one is construction of the shortest one is easy. That corresponds to the just. So in general, we have some long line. The shortest one is just something like this. Operator just two brackets. So that is given by something like this. So this operator is defined by the exponentiation of the electric field, this R. You can also use the L, but it is not so important. So this like this, and the integrating over the some theta, that is the element of the this one. So this operator is gauge invariant. Since the conjugacy class is summing over this element, meaning that this operator commute with any group element. This is a conjugation class. So which means this operator is a gauge invariant operator. So that is this operator. So more precisely, what is the operator with boundary? So there is the endpoint here. So which means the line operator with some boundary. Sorry, this line is not. C is the original lattice, and yellow is a dual lattice. So Wilson line is a line operator on the original lattice, and this operator is a line operator for dual lattice in 2 + 1 dimension. So here is just a 2 + 1 dimension. So more general dimension, this operator is a codimension 2 operator in space-time. So in the case of the 3 + 1 dimension, this is a Lattice operator.
Can you clarify more slightly more precisely what is the theta k versus k sub k? Yes. Yeah.
So this is a SUN gauge theory. So element can be written in the some parameter.
Right.
So that is integrating over this parameter.
Okay, and the k sub k is a generator. Should I think of that way?
Okay. This T is a generator. Yeah.
Oh, okay. Thanks. Okay.
Yeah.
Are the points at the end of this line, are they just magnetic monopoles or two lines in higher dimension?
Yeah, this is actually the Toulouse line operator. And this is not genuine, or this is not topological, so in general.
Endpoints are not topological, but the interior is probably topological.
So in this operator, this line is not topological. So in that sense, not Toulouse operator again. So special parameter So special conjugation
Okay,
class.
I'm sorry, yeah, I see. Okay, thank you, never mind. In general, it's not.
Yeah, this is super general. So let me clarify the conjugation class of game theory. So you can choose some representative. So simple example is 2. So this conjugation class can be written in this form. So you can always you can choose the diagonalized part of G. So roughly speaking, you can parameterize this set representative by using the third component of theta. So you can choose this one as a representative. So this parameter space is actually some kind of U1 parameter space. But you know this. So this transformation can exchange the component of the. So this is just a diagonal matrix. So you can exchange these two parts by using this transformation. So you have to divide these two. So this is the parameter space of the conjugation class of the. So this is the degree freedom of this operator. A special parameter. So there are 2 pi is a special point. So that is the center. So there is a trivial, so it's also interesting. So pi is a center element. That is a -1. So in this case, if you choose the center element, then conjugation class itself is just single element. So in this case, you can just write so in this case, this is just 2 pi I 3. So this is a gauge invariant and unitary operator. So this is Topological line operator between this entity. So this is just a 2 points. So you can consider the more longer one. Then so you can consider the more longer one. Then this is nothing. This line is a topological. And this operator is gauge invariant. So gauge transformation of this operator is actually the trivial, since this parameter is the center. So this generates a kind of center of X in this case. So you can also consider the closed line, closed loop of this one. And if you choose a center element, then that is a generator of the one-home system.
Just to make sure, so you are saying topological loop is an end point of that loop.
Yes, yes.
So in one higher dimension, it's a line.
Line.
But in two line, it's a point.
Just a point, yeah.
Yeah.
Yeah. For dimension, yeah, 3 operator.
Yeah.
Yeah. And if you consider a closed loop, and yeah, 2 plus 1 dimension, that is a 3 plus 1 dimension, that is a closed surface. That is a generator of the quantum symmetry. Symmetry operator. But you can also consider the combination of the Wilson line and Wolfenstein line. That is called in some community, that is called the ribbon operator. That is a mixture of these operators. So these are the invariant operators. So just I show you some the action of this operator onto the space.
So whether this Witten-Gukov operator can be or cannot be topological may depend on the other charge.
Yeah, that depends. Yeah,
Right.
Hamiltonian.
And in this picture, is it easy to see that as they live on the dual lattice? On the other hand, other like local charges are living in original lattice.
Yeah.
Is there a way to see how topological nature of this Gukov-Witten operator is sensitive to the charged operator living on the original lattice rather than the dual lattice?
You mean topological nature is not trivial. So, yeah. So I haven't shown you the general longer line. So if you are so if you consider the for longer line is something like this, then precisely speaking, you can characterize this kind of ribbon, so-called ribbon operator. So if you don't know this operator, then it's somewhat strange operator.
Yeah. What lives on the
Yeah, it's a diagonal part.
diagonal? Yeah, what is that?
Diagonal part?
Yeah, who can traverse between the.
Yeah, shortest Witten operator lives in this form.
But what lives on the diagonal?
Diagonal?
So
This
the
one.
R's live on the dual lattice, right?
Yeah,
The U's live on the original lattice.
yes.
Now, what lives on what connects them?
What? This line?
Yeah, exactly.
This line is
Is there a degree of freedom there?
no degree of freedom here.
Then what does it mean to draw a?
This is just a notation of the
Okay.
this is the shortest group of Witten operator, and another one is another triangle is a different line, and ribbon operator is defined on something like yeah this diagram.
But
And
the things that make this the triangle are just in our heads. There's nothing there. Is that right?
nothing there.
You have a line on the original
So, yeah,
lattice.
ordinary degree freedom just lives on the ordinary. Yeah. So this means the operator acting on this matrix. That is the on this link. Yeah. Yeah. This is and yeah, general line operator something like ribbon. Sorry. Yes, operator. And also you can show you that this operator is committed in the Gauss-Law constraint, and also this operator satisfy the flatness condition, which means that is a topological operator in the topological case.
What is it in the continuum? From the continuum perspective, what are these?
I don't know how to construct this operator in continuum, but yeah, we copy there. Yeah, what I mean, this is some kind of dionic operator.
Dionic? but this book doesn't see that the Wilson line is running here. And the VUCA with an operator, if you go to one higher dimension, it's running in the other direction.
Yeah. But this is 2 plus 1 dimension. Yeah, 3 plus 1 dimension, yeah.
But even then, you have the Wilson line here, and then you have a monopole operator here and a monopole over there. No? Is the endpoints
Is that a closed? I think in the continuum, typically, forget you have to restrict yourself to certain conjugacy classes and representation. Some of them are incompatible.
Yeah.
Because there's some constraint where you
There is a constraint between the representation and the conjugation.
okay.
You can define this operator for any group. Yeah. And this operator actually is something like, so if you have A, B, C, D, F, and acting on this S, on G, that this operation is just gives you the sum. But if you choose some basis of the representation, this is just giving you the sum this factor. So chi. So this is character. Just a trace of the representation matrix. And this is just a normalization. For example, a filter case. This is something like in the U1 case, this is nothing but something like this. So just give you some trivial, not trivial, but in your case, this is some phase. So this is nothing but the transformation coefficient of the one-form symmetry. And this is, since this non-abelian gauge theory, this is somewhat non-invertible, so coefficient is a character. Yes. So these are the operator on lattice gauge theory. So since I have only 20 minutes, so I just skip some application of this method to the so we can use this Hamiltonian and also since these are gauge invariant, and you can do you can solve the gauge theory within some assumption. For example, that we can use some variational under of the wave function. Then you can get some confinement, deconfinement phase transition, and also the Wilson loop has some area row or perimeter row and so on. Now this is just some kind of quantum mechanics, so you can use some technique for the quantum mechanics. So I want to just discuss some last 2 parts. So now we already get some Hilbert space. So I just show you some relation between the topological field theory. And also I want to discuss some dual theory of the non-abelian gauge theory. Okay. So I want to frame that So I want to claim that the Hilbert space of lattice game theory is isomorphic to the Hilbert space of the some TQFT with effect. But this actually this is known out, I guess. But I want to explain what this means by using an into plus one dimensional example. So that's just some simple example. So if you are focused on this kind of lattice system, and the gauge invariant Hilbert space is spanned by the, like this is J1 and J2 and J3. The basis of the Hilbert space on this lattice is given by something like this. So this is what we discussed. So this Hilbert space, so actually the equivalent to the let's say the S2 surface with some three functors. So just focus on the topological place of this gauge theory on this manifold. Then Hilbert space of this one is equivalent to this lattice gauge theory. So if you are familiar with surface code, that is surface code. This is a generalization of surface code to the non-abelian gauge theory. But if you don't know that, let me explain. So this is kind of the boundary that where the Wilson line cannot terminate, but the coefficient operator can terminate. This is the boundary condition of this defect. So we can choose several boundary conditions, but we choose coefficient operator can terminate on this line, but Wilson line cannot. So in this case, if you put the non-Wilson loop here, then since this line supports topological, then you can shrink it. So, which means this operation is trivial operation. So, which means there is no degree freedom. This operation does not give you any degree freedom. But if we have some cycle here and here and here, so that gives you some non-trivial degree freedom. So if you put this operator here, then you cannot shrink. So if you do the transformation, this may be equivalent to this loop, but you cannot never shrink it. So which means this state is orthogonal to this state. So this gives you some basis. So more generally, on this surface, you can consider this kind of operator. So Wilson loop. So since we have some network of the Wilson line, so you can consider this kind of network. So this network cannot be shrink to the point. So this gives you the general independent Hilbert basis. So let's say this is J1 and J2 and J3. So this is almost same. This degree freedom is actually the isomorphic to this one. And or you can choose another basis. Something like this. So actually, in this basis, is nothing but this choice. So different representation just corresponds to the different realization of the Hilbert state. Just these are related. Actually, this and this are related to the unitary operation coming from this F. Well, actually, I haven't said. Actually, this is a unitary matrix. So this and this is just a unitary transformation of the basis. Actually, this is equivalent. So which means Hilbert space of this one is equivalent to this one. So more generally, so if you have some many functions, then this is equivalent to some lattice system. Anyways, some kind of lattice system, something like this.
The specific TQFT?
Hmm?
Do you have a specific TQFT?
So TQFT, this line effect is represented by the FUN something.
Sorry, which TQFT?
Which TQFT? So how to say? I don't know the precise name, but TQFT means some topological, and defect is also the topological.
Is it a ground state generator? And what kind of, what did you say about
This is kind of the ground state.
You thought of as some kind of transilence theory?
Not transilence, corresponding to the BF theory. Yeah.
That's a VF theory.
Yeah, BF theory.
On a Villiers theory? Like,
No, abelian BF theory or quantum double model. But that is nothing but that. Yeah. You can get this ground state imposing in the Hamiltonian formulation. If you neglect the electric term, then find the ground state, then you can get this term. So precisely speaking, topological, since this is a degree freedom continuous, so if you regularize the degree freedom by the, for example, the quantum deformation, or you just consider the discrete gauge theory, then that is really the topological. But continuous case, I don't know. There is some support. But formally you can use this kind of computation. But since this is a action of electric field, so we also have some coefficient operator. So that acts this line, what here and here. This is the coefficient operator. This is the Wilson line, Wilson loop. And also we can obtain the algebra of the Wilson line and the coefficient operator by using this and the commutation relation of the electric field. So in this theory, we have two types of operator, that is the Wilson loop and the coefficient operator, and the matrix element can be written by this operator. Okay. Then we can define the Hamiltonian of this theory. So just consider SU3, SU2 case. So you can consider some kind of Hamiltonian like this. So now, originally we use some E square term here, but I just replace E square term by by using the coefficient operator. This is kind of the approximation. So this operator acting on the two defects, and this operator acting on the some type. Yeah, loop around some defect. So this is the Hamiltonian. So this is almost equivalent to the previous Hamiltonian. So if you expand this operator, so S something like S something like in operator, and if you expand this operator, if you do that, so more precisely, you should choose some or just Hidaka. So yeah, just if you expand the explanation of the E by using the small epsilon, then you will get something like so, which means this is a kind of the regularization of the E square term by using the coefficient operator. So which means, yeah. So this operator just acts on this link. And this operator acting on the something like this integer. So in this,
What is the circle?
huh?
What
circle is this U. This one. Point is this, sorry, this defect. Point. So that is a strong coupling limit. And you can also solve this Hamiltonian by using this limit. And also anyway, you can solve this limit to limit. Let's say this is 1 and 2. The case 1 is nothing but confinement space. So this Morphic operator is trivial. So actually, the Morphic operator is somewhat disordered. If you choose the center element, this is the disorder of the one symmetry. And the ground state graphically written in. So I just for simplicity use this just 3 functions. Ground state is written in this form. This is the ground state of the strong coupling limit.
And what is the continuum limit? What do I do with the first? If I wanted to reach the continuum limit, what should I do with J and K?
Continuum limit. That is weak coupling limit.
What does it mean? Like how do I tune J and K?
J and K is actually the proportional to the 1 over G squared and some, I don't know
So J needs to be small.
small.
So K needs to be large, and then
J should be the small.
Kappa needs to be large.
Yeah.
J needs to be small. So it sounds like the second one.
Yeah, continuum limit lives in this region.
Okay, good.
But lattice has some artificial, not artificial, but have a strong,
That's fine. That's fine. So one is like lattice strong coupling.
Yeah, lattice strong coupling. So what we want to know is this way. In some sense,
But you said you could solve the second.
Second limit on this Hamiltonian can be solved.
But is it in the same universality classes? What do I?
So in this limit, so actually, in this limit you can solve, but that limit is unstable against the small perturbation for J in the SUN gauge theory. Stable against that is stable for the discrete gauge theory, but not unstable for the continuous gauge theory.
And is epsilon a parameter?
Epsilon goes to 0 is a continuity.
No, sorry. There's an epsilon in the expression above, in the definition of the Hamiltonian. Is epsilon a fixed number? Do I get to choose it once and for all? Like
that should be the small number.
Epsilon used to be, so there are 3 parameters here?
Yes, now 3 parameters here.
Okay.
And lattice spacing and
So a lot of spacing is always 1, right?
okay, fine.
So,
Then epsilon and coupling constant. Both tuned to the 0.
that's okay.
And there is couple gauge.
But I'm confused about parameter counting in the lattice theory. So if I set lattice spacing to 1, does the lattice model have 3 dimensionless parameters, or 2, or 1?
Okay, so this is a kind of the modified version of the Hamiltonian. So I introduced some epsilon here. The
Yeah.
epsilon zero limit corresponds to the just the E squared.
Yes.
Then in that limit, we have the coupling constant and lattice spacing. If you choose the lattice spacing we want, then we only have the coupling.
Good. And that much I
Okay.
Yeah, since this is a Hamiltonian formality, so there is no rotation invariant between space and time. So space direction coupling, time direction coupling can be different.
Yeah.
that's yeah.
So roughly speaking, this epsilon corresponds to the time direction kind of regularization. Okay, so it's already 5 o'clock. So anyway, this is a strong coupling limit vacuum in the electric basis, I mean the Wilson loop basis. So you can easily check the so if you put the Wilson loop, the non-trivial Wilson loop, for example, like this, then this state is orthogonal to this one. So this is the Wilson loop. So which means trace of Wilson loop. So this state is nothing but a strong coupling. And so this state is orthogonal to this one because this is not the this is the different state. So this is equal to 0. So this is nothing but just a confinement. And also this state, so there is no electric field here. Then if you apply this operator, so remember this operator just pick up the electric field with some coefficient. So if you apply the some state J, S, it just gives you the something like this. So if J equals 0, that is no electric field, then this is just 1, which means this state maximizes this Hamiltonian. So this Hamiltonian is bounded by 1. So yeah, no electric field is nothing but the trivial state for the electric part of the Hamiltonian. And also you can easily show this is confined. And also you can solve another limit. So with some normalization and some so you can add the Wilson loop on each effect with some special combination. Then this corresponds state. One can show that this state is a eigenstate of this operator. Let's say this part is HE and this is HN. So one can show, so maybe this side one. Well, so minus So in this case. So if you apply this operator on this decoupling state, then you can show that this is minimize. This state minimize the Hamiltonian. So here is the number of the defects. Just correspond to the volume. So we have the two limits of the state. And also this is a basis for the electric line. I mean, the basis is generated by the Wilson line. So that is original lattice, degrees of freedom of the original lattice. So you can go to the dual lattice theory. That is given by the network of the coefficient operator. And you can solve the similar thing by using the another basis. So actually, I don't have enough time to explain that. So in this case, so if you choose a Hilbert space by using this kind of notation, that is a Hilbert space is found by the electric line, the network of Wilson loop. That is the ordinary lattice gauge theory. So if you expand the Hilbert space by the network of the coefficient operator, that is also possible. So previously, I said you can expand the Hilbert space by using the network of Wilson line. You can also consider some network of the coefficient operator. That is also the basis of the Hilbert space. But in this basis, this operator looks like some kind of the matter term. So in the usual matter field, something like this. So if you use this basis, then this theory looks like some matter theory of this operator. And this operator acting on the local vertex. So this kind of duality is known for the abelian space. In the abelian gauge theory, for example, this abelian gauge theory is equivalent to the Ising model in transverse magnetic field. So you can do the similar. I guess so. This is the ongoing work. So you can do the similar things for the non-abelian gauge theory by using this kind of formulation. Then you can get some so non-trivial matter field given by this operation, and this operator just acting on the local vertex. So you will get some dual theory that I hope. This is not well developed, but we will get some matter theory, and also that you can see the confinement phase is kind of the condensation of this degree of freedom. That is the condensation of the magnetic monopole. Okay, that is. Thank you very much.